Hello! In this video, we are going to prove the following theorem. Let an, bn from n equals 1 to infinity be a nested sequence of closed bounded intervals, such that the limit as n approaches infinity of bn minus an is equal to 0. Then, the intersection of all of these closed bounded intervals is a singleton set, so it consists of exactly one real number. Now, to say that this sequence of closed intervals is nested means that each closed interval in the sequence contains the closed interval that comes after it. So, the first closed interval in our sequence is a1, b1. Maybe it looks something like this. The next closed interval in the sequence is a2, b2. Maybe it looks something like this. But as you can see, a1, b1 contains a2, b2. a2, b2 contains a3, b3. a3, b3 contains a4, b4, and so on. This sequence of closed intervals goes on forever. Now, by the nested intervals theorem, there does exist at least one real number which belongs to every single one of these closed intervals. Right? So there is at least one real number in the intersection. We're trying to prove that there is exactly one real number which belongs to the intersection. Right? And so that's going to come from the condition that the limit as n approaches infinity of bn minus an is equal to 0. Right? So essentially what this is telling us is that the difference between the endpoints of the intervals is converging to 0. So visually, there's going to essentially only be one real number which belongs to every single one of these closed intervals. And so that's what we're going to prove. So to start out the proof, let's first note, by the nested intervals theorem, there does exist at least one real number in the intersection. So let's just pick one. I'll call it x0. Now we're going to show that x0 is the only real number in the intersection. And to prove that, we're going to show if x is any element of the intersection, then x has to be equal to x0. That's how we're going to do it. So let's give ourselves an arbitrary real number x, which belongs to the intersection. From here, we want to show that x is equal to x0. Now to show that x is equal to x0, it suffices to show that the absolute value of x minus x0 is equal to 0. Right? If we can show that the absolute value of x minus x0 is equal to 0, well, turns out when the absolute value of any real number is equal to 0, that means the number itself is equal to 0. So this implies x minus x0 itself is equal to 0, and therefore x is equal to x0. So, how do we show that this real number is equal to 0? Well, to prove a real number is equal to 0, we can use the following fact. Let a be any real number greater than or equal to 0. If a is less than epsilon for every epsilon greater than 0, then a is equal to 0. Right? Or another way of putting this is, if a is less than every positive number, then a must be equal to 0. So, we're going to use this fact to prove absolute value of x minus x0 is equal to 0. So, first of all, we know that the absolute value of any real number is greater than or equal to 0. So, absolute value of x minus x0 is greater than or equal to 0. That's true. So now we want to show absolute value of x minus x0 is less than epsilon for every epsilon greater than 0. That will prove that absolute value of x minus x0 is equal to 0. So, we want to show that this is true. And to show that, since we're trying to prove a state in about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. Now, we're going to be using the fact that the limit of this sequence is equal to 0. Because the limit of this sequence is equal to 0, well, by definition of the limit of a sequence, this means the following. So because this sequence converges to 0, this means this statement is true. So for every epsilon greater than 0, there exists a positive integer capital N, such that for all integers n greater than or equal to capital N, bn minus an is less than epsilon. Now, more precisely, from the definition of the limit of the sequence, this would actually say absolute value of bn minus an minus 0 is less than epsilon, right? Strictly looking at the definition, right? But replacing this with this is not a big deal, right? The two statements would be equivalent, right? This just looks nicer than this. So, because the limit of this sequence is equal to 0, this means that this statement is true. So this statement works for every positive number. So in particular, it must work for the positive number epsilon that we have in our proof. So taking this positive number to be the epsilon in our proof, well then there exists a positive integer, capital N, such that for all n greater than or equal to capital N, bn minus an is less than epsilon. So, this statement works for every integer greater than or equal to capital N. So in particular, it must work for capital N. So taking n to be capital N, we have that b capital N minus a capital N is less than epsilon. So instead, I'm just going to say there exists a positive integer capital N such that b capital N minus a capital N is less than epsilon. Right? This is really all we're going to need. Now remember, x0 and x belong to every single one of these closed bounded intervals. So in particular, x0 and x must belong to the closed bounded interval a capital N comma b capital N. And so that tells us that a capital N is less than or equal to both x and x0, which are both less than or equal to b capital N. Now, if we visualize our closed bounded interval a capital N comma b capital N, well then, x and x0 are some points in this closed bounded interval. Maybe this is x0, maybe this is x. Well, there's some elements in this closed bounded interval, but no matter where they are, the distance between them is always less than or equal to the distance between a capital N and b capital N. In other words, what I'm saying here is that it follows that the absolute value of x minus x0 is less than or equal to b capital N minus a capital N. Right? So no matter what points they are in our closed bounded interval, the distance between them is going to be less than or equal to b capital N minus a capital N. Right? That's what this is saying. Right? But b capital N minus a capital N is also less than epsilon. So this shows absolute value of x minus x0 is less than epsilon. And that is exactly what we wanted. So, putting this all together, since epsilon was arbitrary, we have shown absolute value of x minus x0 is less than epsilon for every epsilon greater than 0. So, this condition, right, this condition is now satisfied, so we can now conclude absolute value of x minus x0 is equal to 0. But remember, this implies that the number we are taking the absolute value of must be equal to 0 itself. So that's saying x minus x0 is equal to 0 itself, which if we add x0 on both sides, we get x equals x0. So now let's put this all together once again. We gave ourselves an arbitrary element x in the intersection. From there it follows x has to be equal to x0. that proves x naught is the only element of the intersection. And that's it. This completes the proof. Now, as you can imagine, since this is a nested sequence, it follows that the sequence of the left endpoints is an increasing sequence. So we have A1 less than or equal to A2, less than or equal to A3, and so on. The sequence of the right endpoints is going to be a decreasing sequence. So we have B1 greater than or equal to B2, greater than or equal to B3, and so on. Now, when we proved the nested intervals theorem, right? When we proved that there is at least one real number in the intersection, we ended up showing that the collection of the ANs is bounded above, the collection of the BNs is bounded below. So the collection of the ANs has a supremum. The collection of the BNs has an infimum. We saw that the supremum of the ANs is less than or equal to the infimum of the BNs. And let me just copy these guys and these guys onto what we have right here. So we essentially have this. When we proved the nested intervals theorem, we saw that both the supremum of the ANs and the infimum of the BNs, they both belong to the intersection. Right, and that's intuitively what we see here, right, with the dots. But in the case of this theorem, since the intersection consists of only one real number, well then in this case, that means the supremum of the ANs would have to be equal to the infimum of the BNs. Also, since the sequence of ANs is increasing, well then by the monotone convergence theorem, this sequence must converge to its supremum. Also, since the sequence of BNs is decreasing, by the monotone convergence theorem, it must converge to its infimum. So these guys are all equal to each other in this case, right? But they are all equivalent ways of expressing this unique element x naught in the intersection. So that's essentially what we get. And so yeah, that's pretty much it for this video.